Hello, I'm Brandon Dobie, and today we're going to review projectiles and their vectors. Some vocabulary that you would need to know before we review this section is vectors, projectiles, trajectories, velocity, maximum height, range, and resultant, which I will go over. First of which that I mentioned is vectors. Vectors are a quantity that has direction and magnitude. Vectors can be used to describe forces that act upon an object to cause motion. An example of two equal vectors of force is right here. Notice that the two arrows are both pointing in the same direction. An example of unequal vectors is here. We'll see a lot of unequal vectors when we go into the topic of projectiles. Any object projected into space, into or not, by the exertion of a force, such as this. This can be considered a projectile because I'm about to project it into space with the exertion of force through my hand. You see that path that ball just took? That's a trajectory. See how high I threw that ball? That's considered the maximum height. How far I threw the ball is considered as range. The view that I have in front of you is projectile motion and launch projectile motion. The arrows that you see are the vectors that we just spoke about. See, if you notice the forces that act upon the first one in projectile motion from an object being dropped down. There's forces going straight over to the right, and there's forces pulling straight down. The forces pulling straight down can be considered as gravity, while forces to the right could be an outside force, which also can be measured in terms of velocity if you notice the VP. In the end, there's a middle curved vector that I drew in that shows the true direction of the object. That is what we can call the resultant vector, which I will get into later, and we will show how to calculate these, which will probably show up on the final. If you look onto the bottom, it's almost reversed for launch projectiles. In the launch projectiles, they follow the trajectory of the resultant vector. However, the resultant vector looks different than the first one. That's because there's a force acting up and to the right of it while it's combating with the force of gravity. This causes a parabola, or also known as an arc. For the final part of this video, we're going to do a practice problem. I'm going to write it and show you step by step on how we're going to do it. In this problem, we are given the problem of solving the flight of a ball. This ball was launched with an initial velocity, remember we defined velocity earlier on, at 4.47 meters per second. Make sure you write your stuff down, it's very important. It was also launched 66 degrees above horizontal. So how do we solve the flight path of this ball? Well, first we write out everything that we know. So at this point, we know that x0 equals 0, y0, because it's starting at 0. So its x and y coordinates are at 0 on the x and y plane. So I write this, x equals 0 and y equals 0. Its initial velocity at 0 seconds is 4.47 meters per second. So I wrote that down along with. We have the angle of 66 degrees and the acceleration is negative g. We want to know what y1 equals when vy equals 0 and what the time is. So basically x when y is 0 should be the range. We did this in 2 steps. First step, separate the steps. Notice what we have so far. Are you following, class? All right. Okay. We start out when vy equals 0, t equals vyo over g. So we're using the velocity formula to start this out. Then we write it out. So t equals 4.08 times 9.80. Multiplying by that constant for gravity,
the velocity that was launched out at. And we get a total time of 0.42 seconds. Correct? Now, to find the y maximum height, which we defined earlier, we take that 0.42 seconds, multiply it by its velocity, 4.08 meters per second, subtract it, here's the trick, half of the force of the acceleration of gravity divided by 2 times the acceleration of gravity times t squared. That ends up looking like this. See the minus 1/2 gt squared in the bottom right hand corner. So you solve your basic mathematics and you end up getting 0.85 meters as your total when y is at its maximum, correct? So now we want to figure out where's the ball when it lands, when it hits the ground after being launched at 66 degrees at 4.08 meters per 4.47 meters per second. Well, in order to do that, we do the same equation that we just did, except with 2. So we would do 2 times 4.08 times 9.80, the acceleration of gravity, and we would get 0.83 seconds. We use that 0.83 seconds with the cosine of 66 and the speed, so now we have an equation that looks like this. Our final equation to get the answer to its final landing distance, which we defined as range earlier on, comes down to 0.83 seconds times cosine of the launched angle times its launched speed. So we get something that looks a little bit like this. After we do that, multiply it out, and our answer is 1.5 meters. So, to review, 4.47 meters per second, 66 degree angle, 1.5 meter range. Am I correct, class?
I am, because I know I am. Thank you.